esteemed presenters, come speaker for today's session, and the esteemed delegates who are present here for the session. The session is mining and mineral. With the theme for the session is basically the mining, the developing India's critical mineral value chain for a sustainable future. As all we know, yes, the mining and the taking out the metal from the mineral to produce is nowadays essential. And if we talk about the value chain as well as the sustainable future, it is equally essential for a country to become developed, to have a large resources of this minerals. And the minerals like any lithium, sodium, copper, any metals to that extent, which are used and highly required for the clean technology, which includes the solar panel, like rechargeable battery, the wind turbines, and grid battery storage, etc., etc. So the process of taking it out from the mineral and sending it through the various industrial process is as equally important as it is used in other downstream industry. So let us invite our speaker to go into deep of all these aspects, how to maintain the value chain and as well as go for a sustainable future. We have two speakers today. The speaker one will be Mr. Abhinav Sengupta, who is from PwC. He will be speaking basically on how India can become supply chain resilient for critical minerals. He is a manager in mining and metals of PwC India. And my second speaker would be Dr. Binitha G. He is from HPCL Green R&D Centre, Bangalore. And her topic would be biomass waste derived nano-engineered material for fast charging sodium ion batteries. So welcome to both of you. I will ask Mr. Abhinav Sengupta to start with his presentation first.
First of all, good evening to all of you. I know it has been a very big day and we are just going to conclude the entire session. The topic which I have chosen is basically how to make India resilient in critical mineral supply chain. And first of all, I would like to thank India Energy Week for including mining and minerals as one of their themes in this congregation, because mining is a primary sector in India and critical minerals will play a very important role in this energy transition. So without much ado, let's get started. Okay, so the entire presentation I would like to talk about first, what exactly the critical minerals are, which are the specific minerals I will be talking about, then what exactly the present global supply chain of each one of them, and then we'll come out to the understanding where India stands, and then we'll talk about what exactly India needs and how the factors, the enablers will play a role in this entire journey. So let's get started. Okay, so first of all, let's understand this critical minerals, why they are very important. Now, there are a few things like a conventional an EV vehicle, an electric vehicle consumes more than 6 times the mineral content as compared to a normal IC engine. A solar power plant consumes almost 3 times the mineral content more than a common coal-fired plant. Similar with the wind power plant also, they consume more than 13 times the mineral content as compared to a gas-fired plant. So this is the magnitude of investment that is required in these kind of new energy transition technologies. Now for this current presentation, I'll be focusing on the battery minerals specific, like lithium, cobalt, graphite, manganese, copper. All these are very important. As you can see on the screen, that lithium plays a very important role in terms of cathode material. Graphite plays a very important role in terms of preparation of anode. Similar with the manganese, copper, and you also have nickel and cobalt. So these are the minerals as of now. They are very much important in terms of bringing the energy transition in India. Now it is very interesting to see because these minerals are being mined, and mining is a very archaic way of doing the things. things which is beneath the earth, minerals are always found beneath the earth, and they has to be mined sustainably. So as of now, presently, you could see that the mining is highly geographically centered, and the entire process is fragmented. If you could see on the screen, you would see that China commands the maximum amount of mineral. They do the mining of almost all the critical minerals which we require as of now. So let's say, for example, we have graphite, highest, this natural graphite is highly being mined in the China. Almost all the graphite which is there being mined in China. Lithium they have in the Argentina. Similarly with you also have same with the cobalt. In Congo you will see that cobalt is being mined. Copper is being mainly mined in Peru and all. So you can see that these are the specific countries where these essential minerals are being mined. Now that's the one part of the value chain that is called mining. Now, as you already understand that these minerals cannot be directly fed into the refinery, and it cannot be directly used or say put to use in terms of finished product. It has to be cleaned, it has to be refined, then it can be put to use. So if you go ahead and see that where these mineral processing plants are there, if you could see that this is again geographically centered. China controls the maximum amount of share. As you can see, it has almost all type of refineries, all type of concentration for all those minerals which are listed on the screen. And surprisingly, they govern the major market share, because whatever the minerals are being mined, they has to be brought back to the China. Or basically, if you can see, for Australia, nickel is there. For Indonesia, they have again not Indonesia. You have Congo has the capacity of nickel refining and all. It has to bring to there, then only it will get refined, and then it will be put to use. So this is basically a more peril situation. Now let's understand where India stands in this entire system. So if you plot the entire equation, let's on the x-axis you see that there are certain minerals which have low production and the certain minerals have high production. And the y-axis, if you see that there is a limited demand and you can go ahead with the maximum demand. And if you plot all the minerals which are there in Indian context, then you will see that the topic which I will be talking about, this lithium, battery minerals, rock phosphate minerals, like fertilizer minerals, they all fall in the zone number 4. So zone number 4 is those minerals which are presently low in production in Indian context, but their demand is going to be very high in future as well as present. So this is the present scenario, and now we have to look at the requirement of these minerals in the context of where India is going to progress. Now, if we again see that how to mitigate this challenge. So let's say again we divide this into a 4 quadrant, and what each strategic move we can adopt in respect to each of the minerals. So then we'll see that for the zone 4 minerals which I just talked about, there presently what India is doing. India is trying to acquire equity assets overseas so that they can assure the raw material security. That is number 1, and also they are trying to tie up with some kind of refineries unit outside India so that they can put to use all these all this mineral finished product into their end usage. So zone 4 becomes there has to be a strategic intent for every country at this stage to map their requirement in terms of this raw material security. But when you see all these options, and if I can drill down it to a basic level, then you will understand that there are certain kind of risks which comes with each kind of supply chain. I would see that you can see on my screen that these 7 are the probable options that India could adopt to in order to mitigate, in order to comply with its raw material security for the critical minerals, like buying from the merchant miner, then there is a trader, then there is equity stake, there is the import, and there is the owning and operating and all. And these are the risks which you can see. These are very common risks which are there. So you would appreciate that while we are depending on the import as of now, it has highest of risk in all the sectors. Like all kind of risks are there. Some geopolitical things happen, it will be at the risk. Some supply chain disruption happen, it will be at the risk. And similarly, if you could see that owning and operating a mine, let's say you own your own asset where you mine and go ahead and it has the lowest amount of risk. So drilling down the story, that if you own and operate a mine, it will be better for them in terms of making this supply resilient. Now next, as you already aware, last year 2023, just couple of months back, government has started its first ever tranche of critical mineral auctions. In this they have floated 20 blocks, 16 blocks of the composite license, and there are 4 blocks of mining leases. Now you can see on the screen, if a bidder has to participate in this entire process, it has to wait almost about 7 to 8 years in order to have this final mineral coming out of these blocks, because of so many various reasons. Like as you can see on this composite license, 1 year it will take only for the awarding of contract in this Indian scenario. Then there is an exploration license, then there is a mining lease, then you have to develop a site, you have to obtain a land, then you have to achieve the production, and then you have to match up with the end user refinery. So the stage is quite big. It almost takes 7 to 8 years. So if you start if you start awarding this block in 2024, 21, 25, it will almost started generating, the final mineral out of this from by 2031, 32. And this will only happen if we overcome all these challenges. Like there are seamless land acquisition, there is proper financing, proper financial closure, like also you have end user synchronizations there, and then we can obtain all the clearances, which is the biggest hurdle in Indian context, in time. So that is the problem. So government has, though they have started this critical mineral auctions, but again it will see the light once the first mineral will come out of this block. And this is a very optimistic scenario I have taken. Now going forward, now we have to understand this in detail. Let's map it out, that what are the risks are which are happening in this critical mineral context. So if on the on the x-axis you will see that there are some events which are very likely to happen, and then some events which are extremely likely to happen. And then on the y-axis, if you could see that the impact is low to highest. And if you plot all the reasons for these all things, then you could understand that there are few things like capital. Capital is something which is very important. It has a very highest impact. But now in today's context, when you have so much of influx of money is coming out, you have COP conferences going on, so much of pledges are being taken for the developing nations, this is going to be a less problem. Unlike on the other side, if there is a delay in energy transition, like say some kind of policy changes happen and there is a delay in energy transition, then this mineral mining of these mineral and processing will get delayed. So if you could see that these are the few things like conflict over resource nationalism, who will obtain those reserves, and the lack of capital, or let's say increase in illegal mining. These all are risks, but they are risks that can be India can comply with. But on the other hand, if you see that these risks, that if something happens in terms of delay in energy transition happens, or let's say climate risk happens, like some catastrophic event happened that it stopped the entire world going towards the energy transition, then this will again have a cascading impact on this critical mineral journey. So we have to understand this risk on this parlance. Now once we understand the entire risk, then we have to think about that what could be the probable strategies that India could adopt. So let's see one by one that what measures they can adopt. So presently we are here at 2030. So by 2030, in this context, from the mining perspective, again I'm talking about mining, mineral processing and refinery. What we'll do, we'll continue to mine our domestic resource. I do understand that there are all resources will started operating by 2031, 32. But if for the mining leases and for those minerals which we can find, early operationalization, then this will be there. We will continue to acquire assets outside India, like Kabil has acquired, NMDC has acquired, all those things we'll try to do. Also, we'll focus more on the import. We'll continue to import because we have to comply with our all, the insatiated demand which India has. So this all things will happen by 2030. And at the hindsight, there will be a strong research which will keep on going in this direction. So by 2040, if you could see that we'll go ahead and we'll see that these overseas exploration and overseas mining will turn up to become more of a strategic alliance, where we'll be depending on the other countries only for the strategic requirement, and we'll focus more on the domestic mineral content as well as the refinery, because refinery will play a very important role. And lastly, by 2040 onwards, then we'll have enough amount of research done. Then we will also see influx of urban mining, like end of life electronic waste. We'll try to extract critical minerals from those kind of end of life electronics item, as well as mining. So it will be a mix of both. We'll also have a critical mineral sourcing from the secondary resources. We'll also have a critical mineral sourcing from the primary resources, and we'll try to import based on our strategic needs. But in order to achieve this, there are some key enablers that India needs to focus upon. Priority number one, that is this: mining has to be sustainable. Understand this, critical mineral mining is highly environmentally polluted. You have to adhere to the sustainable standard, number one. Number two, you have to mobilize funds in terms of a lot of investments are required. You require FII, FDIs in this space. Number three, India's entire mining system is having a very high effective tax rate. So you have to thought about some alternate financing mechanism like royalty financing or stream financing or green bonds to cater to these needs. And then lastly, you have to create the data transparency. Like datas are there, but the government is not transparent enough. We have very lack of data, so it reduces down the confidence of the investor. Followed by that, what should we do? There are a lot of price which keeps on changing in the market. So there has to be a proper mechanism in which we can track those prices, and we can convey the same to the government and same to the exchequers as well as to the general investor. We have to make sure that mining has to be done in a sustainable manner. There has to be a domestic development of the region where the mining is done. and also we have a policy dialogues in this. Finally, we should be, since this is a very globally very important thing, there has to be a common ESG platform or ESG standard need to comply with. Like mining happen in Argentina and mining happen in India. For the critical minerals, it has to be ESG compliant. That's something, a common platform has to be maintained. And also there has to be a proper place for innovation, that more robust technology in terms of innovating each technology every now and then has to be there. And lastly, we have to, after doing all these things, we have to make it entirely digital. Like, there's a real-time, there's a real-time tracking of record, there's online submission forms, there's a single window clearance, all those things are required. So these are the key enablers that will enable those measures that India will take. So lastly, summarizing, if you see in all those 4 options, the domestic mining requires a proper focus from the government of India, like they should award some kind of infrastructure status to India's exploration sector, especially for critical minerals. On the other hand, more companies, like more PSUs should acquire more of the overseas assets, like in Argentina, Bolivia, Congo, somewhere, so that they can have that equity assets. Thirdly, we should also promulgate the collaboration between G20 nations in terms of supplying this raw material security in terms of need. And lastly, there has to be a proper research and development. So academic industry interaction has to be there in place that will cater to the need of this. And these all 4 are the enablers that will help India adopting this, these kind of measures for critical minerals. So that's it. This is what a brief presentation was. And I hope with all this, India will try to maintain this critical mineral resiliency in future. Thank you.
Thanks, Mr. Abhinav, for a nice and insightful presentation on your understanding the need for the metals from the raw materials in India, along with describing the demand and supply requirement and the measures which can be taken, adopted to have a sustainable value chain, along with the key enabler. Thanks for the presentation. If anyone has any question, we can ask, or else we will ask. I can request the next speaker. I think Binitha, you can come for the next speak. Our next speaker is G. Binitha.
So, good evening, one and all. I know it is almost at the end of the session, so it will be very few people over there, but I'll not make you bored. I'll explain about the way which HPCL is doing to have a sustainable environment in our Indian scenario. So, first and foremost, thank you, Chair, for the quick introduction, and thank you for my co-presenter to setting the tone of the requirement of this particular one, which it's our humble effort, which we are doing in HPDRDC, which is the title is Biomass Waste Derived Nano-Engineered Materials for Fast Charging Sodium-Ion Batteries. So prior to moving the content, I just want to briefly introduce about my organization. We are from Hindustan Petroleum Corporation Limited, HPCL, which is a Maharatna company. We do have 3 refineries. One is based in Vizag, one is in Mumbai, and we do have an upcoming one which is in Rajasthan. And I am assigned as an assistant manager in Hindustan Petroleum Corporation Limited R&D Centre, which is the Green R&D Centre, and our core purpose is to provide chemicals and energy accessible through innovation. So in this regard, I'll directly move to the work which we are doing. So coming to the content, the first and foremost is a brief introduction of energy storage devices. Specifically, I'll be introducing lithium-ion battery technology and further requirement of a new technology for being a sustainable environment in India, that is the sodium-ion battery technology. Then our effort on indigenizing development of engineered battery materials, then the performance characteristics of the same, and finally concluding with a conclusion and a future prospect on that. So moving on directly to the introduction, maybe all of you might be having a lithium-ion battery within you, because you might be either having a mobile devices or a laptop. Everything do have a lithium-ion battery. So now the technology is even in the extreme dominant condition wherein it can be used even in electric vehicles. So as you could see from the projection from Bloomberg, almost 150 billion of rechargeable batteries are supposed to be there by 2030. That is the market projection. And along that, you could see that almost 187.89 is supposed to be in the market of global lithium-ion battery. Whereas this is another projection from Bloomberg itself. So we should mean that one projection is coming in the last year, like 2021, one in 2022. So we should mean that even in a span of 1 year, there is a critical improvement in the regard or the demand of lithium-ion batteries. And additionally, there is one more thing, which is the global EV market. It has a large market size. It is expected to be at the rate of almost 84 million by 2025. So hardly 2 years is there. Still, coming to the Indian scenario, our EV penetration is not so great. We have hardly 2% EV penetration. But if we are considering the same with China, it is close to 26%. And they are actually leading the market. Okay, so there is a need for either adopting EV systems or even adopting battery technology. Why? Because right now we are in a situation where the demand of energy is increasing rapidly. And also we should have a push towards renewable sources like wind and solar. In order to have these systems in a continuous, uninterrupted fashion, we should have a proper energy storage device. So in that scenario, being in a diverse audience, I just want to quickly introduce on lithium-ion batteries. This is just a schematic illustration wherein it will be very comfortable for you all to understand. So we do have different components of a battery. So it's called anode, cathode, and there will be an electrolyte which holds an ion, which is actually lithium ion in lithium-ion battery, which moves in and out of the structure. So as you could see from the schematic, during discharging, the lithium ions move from the anode to cathode, which is followed by a movement of electrons through the external circuit. So that has been used to typically power our systems. And on charging, the exactly opposite thing happens. So this has been used to further utilize or store the charge, which can be used further from the discharging process. So if we consider this lithium-ion battery technology, though I am said as if this is almost dominating the market, considering the Indian scenario, we don't have much of the lithium reserve. Just like my previous speaker mentioned, actually the critical minerals which is required for a lithium-ion battery is scarce in India. So in that respect, I can see that, as he was also mentioning, there is if we consider this lithium holding countries, you could see from the reserve which is over there, first is Bolivia, then Argentina, then other countries like Chile and also China. But the point you have to mention is, though the lithium reserves are there in these countries, the domination is actually by the Chinese. So though they don't have a reserve, still they are holding the market. And considering the other thing, other raw materials which is typically required for lithium-ion batteries, it is largely towards the different countries. And in India, there is not even a single mineral which I can show over there. The only available thing is manganese. But compare it to getting a better performance battery, it is important to have critical minerals like cobalt, nickel, and also lithium. So considering all these factors, actually, is there a cost-effective and a viable energy storage technology that India can adopt for other than lithium-ion batteries? So this is the critical question which we all should think about. So in that respect, the possible alternative or possible effective alternative technology which India can adopt is actually sodium-ion battery technology. So the material or the technology remain exactly the same. Only thing is that apart from the lithium ion being moving in and out of the structure, it is actually the sodium ion which is transferring. So the concerns are that, I'll come to the concern, but prior to that I'll explain about the positive things. So this is actually a technology, as I mentioned, same as that of lithium ion battery. All the components remain the same except that it should be capable of transferring sodium ions. Another thing is that compared to lithium technology, your mineral requirement is pretty cheap. Like we don't need cobalt, we don't need nickel. Rather, you need some conventionally available materials for sodium-ion battery technology, which actually, in other words, decrease the price of your sodium-ion battery technology. Another thing is that it is actually a drop-in technology, just like lithium-ion battery. So whatever equipments which is required for sodium-ion battery is exactly same as that of a lithium-ion battery. So this, I could say that a lithium-ion battery gigafactory can be retrofitted for a sodium-ion battery technology, so that the price can also be reduced in that sense. And the further thing is that typically lithium-ion batteries has a transport restrictions. It will not be typically taken in flights, considering the fire or the pressure variations which can create some issues in that. So in this respect, actually sodium-ion battery is a potential option because it can be even stored at lower temperature. So the transport issues won't be there. So that these are the highlights of having a sodium-ion battery technology. So further, coming to the actual thing, which is the challenges in sodium-ion battery. So you all know lithium is a pretty smaller element, like your size of the lithium ions are pretty small. But when we compare sodium-ion battery, it's slightly bigger. So as the material or the ions are bulkier, your charge or the transport of the charge is pretty resistant. So you might have some resistance in transferring the ions in and out of the structure. So the main problem associated with sodium-ion battery technology is actually the kinetics, which is in fact, how fast the ion can move in and out of the structure. That is the kinetics part. And compared, whenever we are going for a technology, we'll always look towards the west. Just like even in the US Department of Energy, they are focusing on developing batteries which has a faster charging or a smaller charging time. So in that respect, we have to have a particular material. So whenever we are thinking about a kinetics part, it is actually the material we are contributing to that kind of a thing. So if you engineer your material, you can have a better or a faster charging capability. And for sodium-ion batteries, there is a myriad of materials being available, just like the anode, cathode, or even the other components like electrolyte, or even some binders and other additives which can be used. So engineering each component will have an extreme change in the property of your battery. So in that respect, I have selected as an anode material to engineer it to make to a fast charging capability. So in that, the selection is from the group of materials over there. So considering an anode material, when you take an anode material, you should have a capability to charge or take in more charge with a lower voltage. So lower your voltage, your full device will having a higher capacity or a higher voltage. So it's like you meant to have a higher capacity material which can take out more sodium into the structure and should reversibly give out that sodium into the structure. So from this chart, what I have selected is actually hard carbon. Hard carbon is a material which is actually an hard carbon is actually a engineered material which is a kind of a known graphitable kind of a carbon based thing. And this has been evolved from or prepared from typically biomass kind of materials. So the advantage of this material is it is having a higher theoretical capacity. So theoretical capacity means every material you'll have a capability within themselves that it can store a particular amount of sodium. So here in this case, it is close to 300 milliampere hour per gram. So this another advantage with this material is that it is having an extremely low voltage. So how less your anode voltage is, your full cell will have a increasing energy density. Why? Because your full cell device voltage will be E cathode minus E anode, typical low, which will result in a slightly better capacity. So maybe we can, from the figure, you can just have a feel of your graphite, soft carbon and hard carbon. Graphite will be single layers of graphenes where it will be like layered kind of structure. But soft carbons will be like slightly amorphous or different grain boundaries will be there. But in case of hard carbon, it's kind of a mixed structure. It will have crystalline domains and also amorphous domains. Along with that, you will have some pores also with that. So again, it comes the next big but. So here the problem with the material is that it has a poor rate capability, and also if the rate capability is poor, your charging performance will be there. It will be bad. So what does it mean is, right now we are in an era wherein the energy has to be given in a faster pace. Just like you should have your mobile charged in a smaller duration or even in a span of 30 minutes or even 15 minutes. So we should have such kind of a charging capability in order to have a better battery. So our effort was actually to engineer this sodium-ion battery anode, which is hard carbon, for fast charging or high power capability. So how fast you can charge will be actually a relation towards what is the power capability of your device. So in that respect, what we have actually done is, we have taken a biomass waste, which is actually coconut shell, which has been gone for a particular treatment process, and finally thermal annealing to get a hard carbon kind of a structure. So the process is very simple. Take coconut shell, which is a waste, crush it to a particular particle size, then carbonize it. Then we have to do some alkali treatment to remove some impurities, and finally a thermal treatment to get the hard carbon. And once it has been done, it will be a micron size material. Typically hard carbon will be micron only, and depending about the source, you can engineer it to different shapes. So right now this is a rough morphology, and you could see it is matching with the hard carbon structure from the XRD pattern. So further, as such, this material is not good. We have tested it. I'll come to the results now. So further, what they have done is, in order to have this fast charging capability, what we did is, we did an engineering on this surface. So typically, if a material is having a disordered structure or a surface, your transport will be pretty fast. So in this theory, keeping this theory in mind, what we have done is, we have gone for a disordered surface layer by typically using a transitional metal based material. I don't want to reveal what exactly we have done, but the process is simple. We used a linker. That linker will be added on the surface, and it will be finally, say for instance, carbonized along with the hard carbon to get a disordered surface. So this is directly the electrochemical characterization of a sodium-ion battery hard carbon anode, wherein you could see that the profile is pretty good. You have a voltage which is very low, even less than 0.1 volt, which means that your energy density will be pretty high if we are coupling with a typical cathode material. And when you compare this second plot, which is actually a rate capability plot, we have tested from different rates, starting from C by 5, C by 2, 1C and 2C. So this C means how fast your thing is. Say for instance, if I'm saying C by 5, it's like 5 hours of charging and 5 hours of discharging. On the other way, it is 2C means it's like 60 by 2, which is half an hour charging, half an hour discharging. So which means that even at a fast rate of 2Z, we were able to get a capacity close to 180 milliampere hour per gram. And further what we have done is, battery processing is very unique. You have to process almost 52 parameters in order to make a proper battery. So here what we have done is, we have optimized certain parameters like slurry composition, binder based things, surface layer thickness, even electrolyte optimization, and also the mass which has been used in each electrode. So after optimizing all these parameters, what we have observed is, the same material prepared by the same process is found to have a slightly higher performance. Just like as you could see from the figure on the top, even at a faster rate of 2C, which is half an hour charging, half an hour discharging, you were able to get a capacity which is beyond 225 milliampere hour per gram, and that was sustainable even for 1000 cycles. So the cycling stability is another parameter which determines a battery property. That has also been pretty good in this case. And again at the down graph, wherein you could see that the same is tested at a 4C rate. So 4C means it's like 60 by 4, like 15 minutes charging, 15 minutes discharging. So this is in fact the material being engineered to have a fast charging capability by optimizing the parameters which has been shown over there. So in conclusion, this is actually our humble effort from HPCL in order to have a sustainable India in case of mining and minerals. So we have developed a biomass derived hard carbon, which is actually an anode for sodium-ion battery, and it was engineered to have a slightly higher performance, especially in terms of cycling stability and also rate capability. And this modified materials was found to show high rate capability and also long cycling stability. So that's all from my side. I'll be happy to take any questions if you have.
Thank you, Binitha. Real well articulated presentation with respect to a new development on sodium ion battery, and which is environmentally conducive definitely, and I think it will be economically viable also. My one question is, have you started using it in anywhere?
Sorry, sir?
Have you started using this battery anywhere?
Yes, sir. Actually, we have scaled it up to a pouch level, which means that it's a slightly bigger dimension, close to 4 by 5 by 5. And we have coupled it in order to draw on a cycle, which has been demonstrated in one of the talks, which is already delivered in one of the sessions, which is close 34, session 34.
Thank you, thank you.
Thank you.
Anyone has any questions from audience? They can ask. I think no one has any question. So thanks, Binitha, for a well presentation. Thanks to Mr. Abhinav also. So that's the end of this session. Thank you.